Let's try another problem. An object accelerates from rest to a velocity of positive 17 meters per second. If the displacement of the object during the acceleration is positive 5 meters, determine its acceleration. How much time does the object take to reach its final velocity? Again, an object accelerates from rest to a velocity of positive 17 meters per second. If the displacement of the object during the acceleration is positive 5 meters, determine its acceleration. How much time does the object take to reach its final velocity? Please carefully and accurately copy this problem down and then try the video. And then please try solving the problem using all the systematic approaches and notation that we've introduced while the video is paused. And then start the video up again, please. Step 1, draw the path. Let's say we're starting here and moving here. Now we're starting at a speed of 0 meters per second and reaching a velocity of positive 17 meters per second. So we're already kind of forcing ourselves to choose right as the positive direction, since we've decided that we're moving to the right and they told us the velocity is positive. So we've chosen the velocity to the right. They didn't tell us we were moving to the right, but we can imagine that we are. And now the acceleration, well, we're speeding up again from rest. So the acceleration must be parallel to the velocity. It's a good idea, like we've been talking about, to get into the habit of writing down these vectors. So we've done steps 1 and step 2. The next step, step 3, about breaking into components, doesn't really apply to one-dimensional motion. So it's on to step 4. Writing down our 5 kinematics variables. Delta x, v initial x, v final x, a sub x, and the time. Now we carefully read through the problem and transfer our information. An object accelerates from rest, that's the initial velocity, to a velocity of 0.17 meters. So that's the velocity we're ending up with, our final velocity. Include the sign, please. If the displacement of the object during the acceleration is positive 5 meters, maybe we should have included that in our picture. This displacement is positive 5 meters. Not 5, positive 5. Determine its acceleration. That's a question. There was no question mark on that sentence, but that's a question. Determine its acceleration. Let's put a question mark in for the question. Oh, and they're not satisfied. They got another question. How much time does the object take to reach its final velocity? So there were 2 questions here. Which question should we answer first? It really doesn't make any difference. You can answer whichever you like first. The first question that the problem mentioned was the acceleration, so let's start with that. Now, since we're focusing on the acceleration, we're going to look for an equation that doesn't involve time. We can do this because we've got 3 numbers. When we have 3 numbers, we can pick out an equation. So we're going to start by focusing on acceleration, so we'll look for an equation that ignores the time. V final x squared equals v initial x squared plus 2 a sub x delta x. Start plugging in. We'll use parentheses to help us plug in and separate the signs. The final velocity is not 17. It's positive 17. The initial velocity is 0. The acceleration we don't know. The displacement is not 5. The displacement is positive 5. Now we can get out our calculator to help us here. 17 squared, that's 289. This 0 is going to drop out. 2 times 5 is 10. We need to get the acceleration by itself, so we need to get rid of this 10. Well, the 10 is connected to the acceleration by the operation of multiplication. So we need to do the opposite. The opposite of multiplication is division. I hope you don't need your calculator to do this division. 289 divided by 10 is 28.9. This is not a good answer. We need units. Now, mathematically, did our answer come out positive or negative? Well, we can see that mathematically it came out positive, but because this is our answer, we should show the sign explicitly. This problem was not asking for the magnitude of the acceleration. It was asking for the acceleration, so we need to include the sign. And now we should check whether this sign makes sense. Did we expect the acceleration to be positive? Well, yeah, because the velocity was positive and we're speeding up, so the acceleration should have the same sign. If the acceleration had come out to be negative, that would have meant we made a mistake, and we'd have to go back and find our mistake. So now we can go back up here. Now we know the acceleration, positive 28.9. Positive 28.9 is our acceleration, meters per second squared. Oh, before I forget, there was one thing I wanted to mention on this problem. Remember that all the equations that we're using, they're really only appropriate for constant acceleration problems. These are really for constant acceleration problems, but how did we know that this was a constant acceleration problem? Well, notice that they said determine its acceleration. Well, that kind of implies that this is constant acceleration, because if it wasn't constant acceleration, there would be multiple accelerations at different times. You can't really determine one acceleration unless the acceleration is constant. So this problem really was kind of implying that we had constant acceleration. If they say determine the acceleration, that's implying that the acceleration is not changing, but it's constant. But you know, actually, I think a lot of the time the people that write the problems in textbooks, they get a little lazy about always saying that they're writing about constant acceleration. So maybe some of the problems are not going to say that they're about constant acceleration, but obviously if you're doing problems in the constant acceleration chapter, you're generally going to assume that they have constant acceleration. And the fact is, even if there wasn't constant acceleration, this approach might give us a pretty good approximation. So, but in this case, I think it really was implied that we had constant acceleration because we had determined its acceleration, acceleration singular. Well, there would be more than one acceleration if the acceleration was changing. All right, well, we can't celebrate yet because there's still another question that we need to answer. We need to know what the time is. So now I hope you have this in your notes because I'm going to erase it now.